Okay, and then we are going to find, as we always do, the velocity. This is just a regular velocity, okay? So in order to do that, we're going to call the angular velocity, and then of course your distance, and that distance is the distance between the origin, yeah, and a point on that body. We always do that all the time. So when you study, you should get it, okay? So this is our original angular velocity, and this one is our acceleration, again angular, because you can identify that by Greek letters, okay? And here we want to find the regular velocity, okay? Regular velocity. Why do we have to find the regular velocity? Is because your body is moving, okay? This body is rotating, but then it's also, that rotation itself is already a movement anyway, okay? And that's all. That's the reason why. Then of course our regular acceleration, you're going to use your angular acceleration, the distance between your O and the point P, another angular velocity times angular velocity times that same distance, okay? Since we're using formula sheet, you don't have to remember it, but you should be able to calculate the regular acceleration and regular velocity by using the angular velocity and angular acceleration all together. You have nothing but that 2 and the distance, because we are always trying to find, alright, these quantities by using this axis, okay? Where your axis of rotation they meet at that point, okay? And of course we always take a point on a body for us to be able to understand that rotation, okay? Alright, this time what are you learning? Don't get so much into it, alright? I just want you to get a big picture of it. Then we're going to take a look at the angular velocity, okay? And the same thing, we're dealing with a rotation in this case. 2 components, okay? Instantaneous little ones, therefore we can be able to treat them as a vector. Of course, mathematically we can add them up, right? Why? Because you're dealing with the small changes right there. And of course we are studying, alright, this rotation in 3-dimensional space. So therefore we have our x, y, and then the z axis, alright, 3 of them very distinctly. Chapter 20 and 21 are dealing with the 3-dimensional stuff, yeah? So therefore you have the last axis, which is your z, is also in it. But we're dealing with the same thing, rotational, stuff, which is your rotational velocity, which is angular, velocity, and angular acceleration. Of course, the vectors again is measured from a very fixed point right here, because without the point, it's really difficult for anything to be measured. So therefore, we always have to start with a point to measure something. And then of course you can also measure from a different reference, which is your translating rotating system itself. Alright, this is just showing you how it is moving, and we call it the moving frame, because you're studying again by using axis, XYZ axis, and of course we're treating A as your vector, and of course you're going to sum them up by using these 3 axes. Since you use I, J, and K, here 1, 2, 3, just go very slowly. So you have your I-axis is your, on the x-axis, which is your I vector, and J is a vector on the y-axis, and then K is a vector on the z-axis. So when you add them up, of course, this is your vector, and you can be able to break them yeah, break it down into three components like this. So we go A, yeah, your axis is x, so therefore the vector I, and then you're going to add them up together, yeah, a y j, and then a z k, add them up, and you're going to get your resultant A, okay, your vector resultant A. Mathematically, we call it, we're taking the derivatives, right? Since some of you haven't done the derivative stuff, we can just go conceptually for this class, yeah? Alright, and of course we come into magnitude, yeah? This is vector, because if you look at it very carefully, you can see the bold, yeah? The A is bold, so therefore you know that you're dealing with vectors. Now you're dealing with magnitude only here, yeah? Because we're taking the derivative. Remember the little dot, yeah? Is the derivative mean like the small changes. So when you're doing the small changes, we can just go ahead and do directly with the add them up like the magnitude, you know, treat it like a magnitude. And that's because for little tiny changes, of course, your direction doesn't really change with respect to the moving reference, because the change is so small that you can't really notice. All right, just moving this thing on. Okay, so you can't really notice, yeah. You can't really notice the change because the change itself is so small. So therefore, the directional change is you can ignore them. Yeah, so that's what's talking about here. So here we're dealing with vector. The changes are regular. This one you're dealing with derivatives. The changes are very small. So therefore, we're going to treat it only magnitude. Okay, treat the vectors with only magnitude. Here is, of course, we do the vector as a vector summation right here. I am not going to ask you any of this, all right? If you get a big picture, you're okay with that, and just study the quiz, please, because this is too much for you. But right now, this is like we have a different, yeah, a different scenario here. When you take the derivative, yeah, and then you take the derivative, yeah. Derivative means like we're looking at the change in a small interval, yeah, of time. So when you read like the time derivative, don't feel bad about it. We're just looking at these little changes in a small amount of time. That's what we're talking about it mathematically. Okay, so when we do that with respect to the fixed frame of reference, yeah, we are going to count the direction. So therefore we put in, see, look at the vector components, yeah, right in there. Why? Because the direction of these ijk vectors are going to change, yeah, depends on that rotation axis. Okay, so you have 3 rotation axes. Translations and rotations are 2 different things. Rotating is going around like the translator and move the whole thing, yeah. So here you can be able to see 2 things going on. One is a regular, see, no dot, okay, and then the other one is, see, the major vector, which is your A, yeah, showing you the axis, see, x, y, z. They have small changes, only magnitude, and the other one is, okay, with the direction components in it, okay. So don't feel bad about it if you know, oh, there's another scenario where you take the direction into account, yeah. At that time, of course, we're looking at the little changes in a very small amount of time with respect to a fixed frame of reference. That's about it, okay? Then you think about the derivative of your vectors, yeah? This time you're gonna think about the unit vector. I is a unit vector because we call it a unit because there's only one unit. The magnitude of I is just 1, yeah? This is just looking at its derivative, which is like di, yeah, by dt, mean like you're looking at the small changes in a small amount of time for that vector. what it wants to say is, right, that small change is going to be in the diagram. When you try to find, oh, where is it going, you can see that it's just a tangent, yeah, to the path right here, yeah, tangent, and it is going from here at one time, and the other one is change, little time change. So it's going from here to here like that. Okay, so here D, this little D is showing you that there is a small change from here to there for that vector. Okay, so if you define that, you can be able to write it mathematically in this way. Okay, 1 unit, your omega. Okay, and that's because we define this as a rotation. Yeah, so when the rotation happens to a unit vector, you're going to get a small change like that. That's all it said. Yeah, so when you look at it, it's the same thing for J. Of course, K, it's just telling you, hey, I'm rotating and I have a little change. Yeah, for a unit vector, that's what it's saying. I am rotating. See, because that's a rotation. So that is over here. I am rotating, and when I rotate, I make a move, a little move in a little time. Yeah, and when we represent little changes, we use a little dot over, yeah, on the vector. So that's what it's talking about. Yeah, rotation has happened to a unit vector k, and the change is that. Diagram, when you look at it, we show the change from here to there. What is the change from here? Is at one time, meaning like one reference. Yeah, because the event is right here. The second event is there. So the first event, second event, the second event can never come before the first event. It's gotta come after the first event. So you have two events now. So the first event is before the second event, and we call that the change in time is from first event to the second event. When you measure it with a device, you got that. Yeah, so we call it change in time. That is a difference. Yeah, so the first event, there's not small time add to it. Second event comes and you have a little time, meaning like from here to here, after one by 1,000 seconds later, yeah, this little change happened to it. Yes, that's all. Why do you have this change on that body? It's because of this rotation, and we call it that rotation is omega. Yeah, another Greek letter. Another equation. This is again telling you something about your translation or rotation frame of reference. Reference means don't feel bad about this. It's just telling you like this is how we're gonna measure from this reference. Yeah, your movement, there's rotation and there's translation, moving around and also move in one direction. Yeah, in this case it's going that way. Resultant is we break that down, that rotation and translation into this way in order for us to be able to understand the direction and the magnitude of it. The magnitude of the movement of that body is important because you can't be able to calculate the force and things like that to apply in real life situations. Okay, so here when you look at it, you know that you're dealing with the components. Yeah, at least you got to get that. You're dealing with a resultant vector. You're dealing with the small changes of of that body, and of course the vectors are pointing from a point on that body. And don't forget, these are foundations, and we're breaking down into each unit, and so it's easier for us to be able to study. Okay, and we're dealing with the small changes like that. The small changes happen in small time. So small is defined mathematically. The changes are defined by this little symbol d, which is your derivative we're taking. Okay. So in motion, what you need to know by looking at it is you should know by looking at this equation, there is a rotation because of this symbol. There is a translation because of this axis right there, and the vector. Yeah, meaning like when you have this rotation, and that rotation is gonna change the direction of that vector. Yeah, and of course the vector, the change in the direction translation is being calculated by using XYZ references, because without the references, again, you can't be able to get the magnitude or direction or any of the components that you are trying to understand about that resultant vector. Okay, and if you don't have that change, meaning like there is no rotation, that's telling you here. Okay, if you don't have any rotation here, that's going to be completely zero. So you're left with only your small changes in that vector A along the XYZ axis. Okay, so that's what's talking about the change. Yeah, the small change is going to be only what you are looking at that vector from XYZ axis. Yeah, it's just formally talking about it. We're just looking at how a body is rotating as it rotates, how it's been translated. Yeah, and how we study. We're taking a point, a hypothetical point on that body, and then we're gonna reference it. Yeah, you have only two major points. One is the point where all the x's cross, O, and the other one is a point that you pick on the body, P usually. You can give any kind of symbol, doesn't really matter. Yeah, and you're looking at how the body rotates along these axes and how it translates. Yeah, and represented by the resultant vector here. Yeah. Now after translation and rotation, now we are coming into the third one, which is your general motion. So for general motion in a three-dimensional world, yeah, we are going to deal with the same thing, which is your angular velocity, yeah, and your angular acceleration. Angular velocity, your little omega, and then your angular acceleration is your alpha, yeah. And of course, you understand that for 2x's angular velocity, and also, yeah, in the previous chapters. So anyway, so here is your axis, angular velocity, happening instantaneous, yeah. So therefore, we call it instantaneous axis of rotation. Your motion is rotation. And of course, general motion, you have two things going on, you know that. And of course, your acceleration has a different direction from your angular velocity. And all of that, in this case, we're taking a different symbol. Yeah? So you have you and I get confused. Anyway, so we have a different symbol. Instead of O, now we're using A here. And then instead of point P, we're using the B here. Of course, we're going to break it down the same way, which is your x's, your x and then y, and then your z. Okay, and here are three vectors. One is for the angular acceleration, the other one is a regular acceleration, and the third one is regular velocity. Okay, so you have two velocity, rotation, regular, two acceleration, and you have angular and regular. Okay. Why? Because the motion that you're dealing with for that body is a general motion. So you consider rotation and translation. We call it relative motion analysis. It's just a big name. Analyzing me and trying to understand what's going on. Relative motion means you have two different motions going on. Yeah. Translating coordinates your XYZ. Okay. In order for us to be able to understand that relative motion. So now why do we have to do 2 points? Again, because in a body you have particles. All the particles are not, again, permanently bonded. And they, as the body moves as a whole, inside they do. Okay? And now we put, for calculation purposes, we're going to pick only one single point, because you can't deal with all the gazillions of points inside of your body. Yeah, body means this is any body. Okay, this is just some material, yeah, made of this shape of this body in this example, of course. And we're just picking a point out there and say, hey, this point, on this body is moving, with a velocity v, and because it's moving with a velocity, there is acceleration, for that point. And if you know this point, you can be able to get, the quantities of the motion for B. That's what it's saying. Okay, how do we calculate motion quantities? Motion quantities are your velocity, acceleration, angular, and also regular stuff. So how do we calculate these quantities at that point? We use the relative motion analysis, because the motion is relative. When this move, that move. When that move, this move. When this move, so many other points in that body also move. And they're all moving together, okay? So that's why if you know the velocity of one single point, you can be able to use the relative motion analysis to get the motion aspects or motion quantities, of the other point. That's what it's talking about. That's all, And how do we do it? We use the x, y, z axis. We use a unit vector. Unit vectors are very important because we're counting with one. Okay, so you can be able to do the mathematics easily. Now, since we know that we study the movement of the body in rotation and translation, but picking a point. So when you look at the point that we call that point a base point. Just a point that you pick on the body, in the body. So we call it the base point. And of course, you're dealing with the 3 dimension, so x, y, z. We call that the coordinate system. And the x, y, z is you are putting it, on the point, your base point that you're choosing in order for us to be able to calculate the motion aspect of some other point in that body. You have to place the origin at that point. Otherwise, you can't be able to analyze anyway, relative motion for this, the other point. So therefore, you put the origin at that point, and we call that the translating coordinate system, okay? System means you have more than one part. Now you have 3 parts, which is your x, y, and z axis on that point that we're putting to analyze everything that we want to know of the motion of all other points, each point. Of course, in this case, we pick only one single point, which is B. So now the base point becomes a fixed point because that's the point where all of your axes cross. See that? So the motion, we want to get the motion at the point B right here, and you can measure it, from A, so then you put an observer at point A in order for us to be able to measure all the quantities of motion that we want to get at point B. And the way that we do is the same as the rotation of the body, about a fixed axis, because this is your body and that is a fixed point where all of your axes are crossing, okay? And our aim is to be able to find the stuff that we want to know about the motion at this B point. So we are going to use this as our reference to get it, to get things that we need for that point B, We're dealing with the instantaneous stuff because the change is very small. So instantaneous axis of rotation, because it rotates a little bit, for a while, and we can be able to get the relative motion. And relative motion is happening because we're dealing with the 2 points right there. One is where the velocity and acceleration we know, and the other one is we'll try to attempt to calculate what they are at this second point. So we write our regular velocity, B, at point B, relative, meaning like this little line right there, telling you, hey, I want to know the velocity right here. I knew the velocity at that point A, but I want to know the velocity at point B. So therefore, we are going to get it by using the relative motion analysis, meaning like we're going to use a reference, velocity at A to get the velocity at B. So that's what it's saying here. I want to get the velocity at B by using A, okay? Velocity at A. And now we're going to throw our angular, of course, velocity. Since we're dealing with the angular velocity, you have a total, distance, distance between A and B. Your distance always is between the 2 points, 2 reference, and 1 reference point, 1 the point that you want to get the stuff for. So here, see that little R right there? So you always have a velocity and a distance. Velocity and the distance is going to give you the regular velocity. So angular velocity and the distance between the 2 points you're dealing with will give you the regular velocity. At least you have to get that, okay? Regular acceleration at point B can be calculated by using the regular acceleration at point A, because the reference point, your base point, is A in this case. We're going to use the angular acceleration and then the distance between the 2 points, A and B. Okay, one is the origin and the other one is the point on the body. Of course, since we're dealing with the acceleration, you have to bring your angular velocity stuff as well. So your angular velocity times angular velocity times with a distance, okay? Throw it in and add them up and you're going to get the acceleration, okay? So don't forget that velocity, easy, angular velocity and the distance. Acceleration, angular acceleration and the distance. But in addition to that, you have a little change as well, because your acceleration also have another axis, which is this guy right there. Not only this translating coordinate system axis, you also have your body rotating. So therefore, we're going to bring that up here, which is your angular velocity. So it will go multiplication is because because when you deal with the acceleration, it is based on how your body is taking the distance, in a time, and then you are dealing with the time square, which is like distance divided by the time square, So therefore, that is what we're accounting for, the amount of it, yes? A little bit difficult for you to be able to see it, but you can be able to see it, because if you use only one time for the angular velocity, when you deal with the distance, you're going to get only 1t, because angular velocity is equal to your distance divided by time. So for acceleration, you have distance divided by time 2 times, squared. So time you have to have time multiplied by time, okay? Otherwise, it will be difficult, because remember, our unit is distance of meter per second square, meaning meter divided by time, and then time is in this case second, and then another second, So let me write that down for you if you cannot be able to get it in your head. Your acceleration, you have a distance here. Sometimes we use, since we're in rotation, sometimes we use a distance like that for the theta going around the path of the circle. And then you have a time, okay, square, so this is what I'm talking about. So if you use only one angular velocity, you would have only one time here, So you've got to use 2 of them, and this is what we're doing. Otherwise, again, like I said, you can add only apple to apple. You cannot add apple to orange. If you have orange, you have to translate back to apples in order for you to get the apple. So this is apple. That is apple because that's acceleration. This is velocity. So you have to calculate in order to turn this angular velocity into acceleration. Otherwise, you can add them. So that's what we're doing here mathematically, if you look at it. So therefore, you will be getting distance divided by 2 t's. Okay, that's a t square. Yeah? Okay, don't forget these things. All right, then let's go into another one, which is we're still in translating exercise. Okay, relative motion. When we say relative motion, we're looking at one thing is moving and the other thing is also moving. Motion in motion, okay? Motion and motion happening in the space. So there are so many motion going on. Like the Earth is spinning on its own, and the Earth is orbiting around the sun, and the Earth is moving in the galaxy. They're all relative. That is what we're talking about, okay? You may be rotating, but the entire rotation may be translating at the same time. Yeah, that's what we're talking about. So relative motions are, they're related to the absolute motions. Yeah, so now we're looking at this motion aspect in terms of velocity. Okay, so your velocity at B is equal to velocity at the point A, and you can add it up when you take a look at your velocity B relative to A. Okay, and your acceleration B is equal to acceleration at A plus acceleration at B relative to acceleration at A. Okay, so that's what we're talking about. Because your acceleration at B point cannot be absolute acceleration. Why? Because the B point is moving with the point A, okay? Because they're situated inside of the same body, and the entire body is moving in rotation and also in translation. Okay, so anyway, so that's what we're writing here. It might be a little bit difficult for you right now at this level, but then as you study, you will get it. Okay, and I'll try to teach you how each point in the body is on its own. Okay, like all the people are on their own, right, all over the world. We are moving with our. So if you imagine the entire Earth, the entire world as a rigid body, yes, everything on it, in it, are also moving. Yes, we are. Yeah, we are on that body. We can say, well, I am a point and you are a point, and you're moving and I'm moving, and we are on the Earth, aren't we? Right? So that's how you gotta look at it. Okay, so I can draw it out for you here. This is the world, let's say, and then here is you, and here is me, and here is your friend. Here is another friend. You're moving on your own. The Earth is moving on its own, but we both are moving together, and that's what we call it, relative. Yeah, and we have our own velocity. Yes, the velocity of me, I am A, and velocity of you are B. Okay, and you're moving, and we're all on the same body, yeah, which is your Earth right here. So therefore, where you move and where I move are relative, motions to each other, and that's so your velocity and my velocity, we are like that. Okay, get it? I want you to get it generally. Yeah, I believe that you're getting it. Okay, so now we will get into absolute. Okay, how are we gonna do that from relative into absolute? So absolute velocity, you can be able to find it this way. So the absolute velocity. Now we're picking a point B. In this example, you can get it by using the velocity at A, and then you're gonna add your angular velocity times r is going to be translated into a regular velocity. That's a regular velocity. The whole thing is a regular velocity. So you can add the two velocity to produce a regular velocity at B. Okay? Regular velocity at A plus angular velocity times the distance between that 2 points is going to give you another regular velocity. Okay? And so what is this thing that is a little more than the velocity at A? If you add this, you're going to get the velocity at B because they are r distance away from each other. Yeah. So I'm going to draw it here again for you. Yeah. So here is your point A, here is your point B, and this is your A right here. There is a velocity at that. We want to find the absolute velocity of B. We call it regular velocity. and they are r distance away from each other. Yeah. Therefore, if you want this thing, you're gonna add this plus what happened around here. Yeah, and this between them. So what happened between them? There is a angular movement, which is your rotational movement, producing the angular velocity right there, that distance away. Now we are adding that to it. So you have your velocity at A, and then we're going to add the movement is rotation, okay? So therefore we have angular velocity at that distance away between that 2 points. So if you add this little one to this, you're going to get the velocity at B, okay? Pretty easy, yeah? You have to make change in order for you to get a new one. That's the original one. Change is that. This is a new one, okay? Event 1. Something happened in a small amount of time. What happened? It rotates, okay? And after that, you get second event, which is that thing is moving with this velocity instead of that velocity right there, okay? That's all. We're going to do the same thing to the absolute acceleration at B. You initiate it with the absolute acceleration at A. Your change is angular acceleration, distance r away from each other between that 2 points. And then you have angular acceleration, distance r away from each other between that 2 points. You also have another one, which is angular velocity r distance away from each other. This is acceleration, that is acceleration, and that is acceleration. You add them up, so you will get the final acceleration, okay? So that's what's going on in here. First event, second event, third event, okay? You add them up, you get this, okay? Don't forget, they are vector. You're dealing with the vectors. Direction, yeah? And we're dealing with the motion, okay? Motion, but we treat them as vectors. Okay, this is a little bit hard for you because we're like doing three-dimensional, because sometimes you have some issue trying to deal with the small changes, because your angular acceleration is going to measure your magnitude, yeah, that's a value, and also the direction, because we started out with a very tiny little derivative, meaning like the small changes, and then all of a sudden we attempt to calculate the regular, which is your absolute velocity of that body, by using tiny changes of a point inside of that body, okay? So at that time, we have to deal with the direction of magnitude again, yeah, for the absolute thing. So it's a little bit difficult when you have to do with 3 axes, okay? Okay, so we deal that difficulty by simplifying it, okay? So we do the direct solution, which is your regular or absolute velocity at B relative to A. You can be able to get by taking the original one out of the final one, okay? So if you want the relative, you can be able to get the final velocity minus the initial velocity, okay? And you will get the change of that. And again, your relative velocity, your angular velocity times your distance, yeah? This is your relative anyway. Because of that, final is the velocity at B. You started out with velocity at A. The change happened because they move, yeah, relative to each other, and that's what we're talking about, yeah. So you can turn that back to the original one, which is what you can be able to see, yeah. So this one come from the original is velocity at A, yes. Now it's like we're moving this thing to that side, yeah. And then you have your change, which is your relative, yeah, velocity at B relative to A, okay. And if you add this, you're going to get the final absolute velocity at B. Okay, now we bring this thing to that side, yeah, which is what we're writing here, yeah, and that's what you get. So I can do that for you. Actually, I should write it this way for you, easier, yeah. So I'm going to bring this to that side. So when I brought that, you get the equation that you're seeing, yes? So minus, and that is going to equal to this relative, yeah? Velocity of B relative to A, okay? Which is this, yeah? The same thing. And for direction, of course, we deal with the cross product for the vectors, and don't worry about this. Yeah, this is just not the regular multiplication. That's just cross product. It's just trying to tell you that this motion, yeah, relative motion, velocity, so the absolute velocity of B relative to A, that is actually perpendicular to the distance, yeah, between that two. We're just trying to locate, you know, where that vector, you know, velocity vector is going. That's all. So, anyways, I don't want you to get into any of it. Yeah, it will take some time for you to get it. Just know about this much is fine. Yeah, how you ended up with the final from the original by doing a change. Okay, which is this one. Then of course you derivative mean we're looking at the small change, yeah, time derivative, small changes. We're still doing the cross product altogether, yeah. So if you add them up, of course you're going to end up getting 0 because they're perpendicular to each other. So when you do the cross product, it will definitely give you 0, and this is 0. So therefore, so another equation is also going to be 0, and that's just for you it will be very difficult for you to be able to see it right now. It's just like when we do the cross product for the velocity, yes, relative motions velocity, and also the acceleration, yeah, relative motion acceleration with that distance away from each other, and you add them up, you will definitely get 0. Okay, it's just telling you I'm just going to make it as easy as possible for you. It's just take a line if they're perpendicular, the cross products, yeah, for velocity and also acceleration is going to give you 0 in value. That's about it. Yeah. Well, I won't be asking you this. 20.4 all the way to the end is not necessary for our class. So all you have to just read them. I'm not going to go over it. It's just getting more and more complicated for you because we go down into very, very small changes. Yeah. So I really want you to read only up to 20.3 and 20.4. If you have time, you can read it a little bit. It's just like we're breaking things down, yeah, and going into different position, and of course you're dealing with a more and more complicated mathematics, yeah. So therefore we won't be doing it for this semester, but I will definitely recommend you, if you have time, yes, you can read it. Okay, if you don't have time, don't worry about it, but definitely read, yeah, from 20.1 to 20.3 and try to get the concept of it. Okay, and if you do have time, read all the way down. Yeah. Okay, so let's go to chapter review. You definitely need to know the rotation about a fixed point. Yeah, your fixed point here, another point in the body, your angular, okay, velocity, rotational axis, your angular acceleration, rotational axis. These axis has a common point, which is your O. Okay, you can get everything that you want to get at a particular point, which is the r distance away from your reference point. Okay, by doing this, yeah. First equation, second equation, looking for the regular, yeah, velocity, you can get it from angular velocity. Regular acceleration, you can get it from angular acceleration. And we play with, of course, the distance between them. Okay, don't forget you need the change in order for you to get the final one. All right, so anyway, so make sure you study the rotation about a fixed point. Then, of course, your general motion, we covered that. Yeah? This one's just for reading. Okay. All right, that's it for this chapter 20.